Welcome to the final lecture of Week 7. This is Lecture 7C. We're continuing with mechanical considerations. In this case, we're going to look at energy savings derived through the use of economizers on air handling units. So review an economizer is a way for air handling units to bring in outdoor air to cool or assist in cooling a building. Now, this is extraordinarily dependent on the appropriate outdoor air conditions, so there's a wide range of variability there. And again, we're not dealing with just temperature in this case, we're also dealing with humidity. So we have a total heat or an enthalpy situation that's crucial. So bottom line is here that economizers work best when we get to take a look at both the outdoor air enthalpy and return air enthalpy when we can measure those two situations. So economizers, really we have three generalized sets of controls that economizers come with. The first one is a complete standalone control. The economizer has a switch that's set manually. It pretty much will do or put the dampers in a position, and that's pretty much the end of it. So that's the first or most rudimentary level of economizer control. The second type of control, the economizer, is enabled from the air handling unit's local controller. In other words, the economizer has its own rudimentary controller, but it's simply not set by a manual switch. It may have a set of parameters already built into it, but it needs an enable signal from the air handler's unit's local controller. So this gives us a little more control over when the economizer operates or not, but it's still not ideal. The final set of economizer control is when we're in full control of all the associated dampers. So we're in full control of all the air handling unit dampers. The outdoor air dampers, return air dampers, exhaust air dampers, we're in full control. And we're talking about analog control where we can modulate the dampers to specific positions. Economizer saving potential. The first one was where we completely replaced mechanical cooling when the outdoor air is suitable. And the end result is the savings in the mechanical cooling not having to operate. Now remember, we're still running fans. We still have to circulate the air. So by no means is this a free cooling situation. It's sort of a misnomer. Economizer, well, there is no such thing as free anything. The second situation, the control system checks the outdoor air and the return air enthalpy to see which airstream has the least amount of energy. And once it decides on that, it'll mechanically cool the airstream with the lowest energy content. So if you have something going on internally in the building where there's a high amount of energy being dumped into the airstream, frequently the outdoor air, even though you would normally look at it and say, wow, that's too hot to use for economizer, it still may be less energy intensive than the air that you're trying to get rid of out of the building. Again, if you're checking enthalpy of both airstreams, it may be more beneficial to mechanically cool the outdoor air than the return air, depending on what was dumped into it from the space. Simple manual calculation. We're going to use correlation weather data, which is in your weather packet. We're going to use simple outdoor air dry bulb changeover. So this does not use a complex enthalpy type situation. We're going to use estimated cooling savings in BTUs per every 1,000 CFM. And then we're going to estimate for 50 hours per week operation. So these correlation tables unfortunately have to come up with some sort of starting point situation. So this doesn't mean that we can't use it for a slightly different situation. It just means that the equation is going to have correction factors in it. Now, let's go and look at the correlation weather table. We're going to be using columns J and columns K from the correlation weather. Column J is the changeover temperature, the optimal dry bulb temperature where they're figuring that Economizer would work or not work. The next thing is using this optimal dry bulb outdoor air temperature. These are the typical or potential cooling savings. In this, like for Grand Rapids, Michigan, we have 13.7 times 10 to the 6th BTUs per every 1,000 CFM that we have. So that's how that's read. Now, this is based on a 50-hour per week operation. So let's look at the formula. The formula of the calculated energy savings is the total recirculated airflow minus the minimum airflow times the hours of operation per week, the actual hours of operation per week, times the estimated annual savings, times the kilowatt hour per ton, that's our cooling, we talked about that in the last lecture, times the cost per kilowatt hour, and that's our 10 to the 6th. So don't put this in twice. If you put the annual energy savings, like we looked at just a second ago for Grand Rapids, Michigan, that was 13 point something, that 13 point something was actually times 10 to the 6th, and that's where that shows up. Don't put it in twice, and don't forget it. Now, correction factors. Again, this savings is based on per every 1,000 CFM, so we have to divide that out. It's also based on 50 hours a week, so we actually put the actual hours of operation per week, and we have to divide it by what the equation was originally meant for. So the 1,000 and the 50 are correction factors based on what we're actually doing. This 12,000 are the BTUs per ton of cooling. Now what I want to back up here is let's look at this. Total recirculated airflow minus minimum airflow. This is the total CFM that our air handling unit is using. We have to subtract out any air that we're already bringing in for ventilation air. We have to bring that in anyway, so we can't count that as a savings. We're already bringing it in to meet ventilation or indoor air quality requirements. That's something that was already being brought in. So that has to be separated or subtracted out of the total airflow. So here's our example. We're going to use Grand Rapids, Michigan. I have a fan on a main air handling unit that uses 40,000 CFM. It's got a minimum setting when it's bringing in ventilation air of 4,000 CFM. It operates 48 hours per week, and the equipment uses 1.24 kilowatt hours per ton of cooling at a cost of 11 cents per kilowatt hour. So when we plug that in, this is our total air of the unit minus the minimum outdoor air that it's bringing in for ventilation times the actual hours per week of operation. This we got from our correlation weather table. That was 13.7 BTUs per year times that 1.24 kilowatt per ton times the cost times this value to the 6th. Then we make the corrections, the 1,000, the 50, and 12,000 BTUs per ton. So when we run all those numbers, we get a savings here of 5,381.80 per year. So again, remember, the 50 corrects for variation in hours of operation. In this case, we were only running at 48, so the 48 over 50 is actually a fraction. It adjusts this by a certain fraction. Same thing on the CFM. The CFM corrects for variations in the amount of CFM. So again, that correction factor is subtracting out ventilation air that's already being brought in. We can't count that twice. This ends all lecturing for week 7. When you're ready, you can proceed to the assessment for week 7. Thank you.